Hi again. So now we will demonstrate that cosine chi pi equal to negative 1 to the power k. Okay, so let me see now. We will prove that cosine of a number k times pi equal to negative 1 to the power k. Okay, so how do we do this? The first thing we need to do is we need to have an expression for cosine of x from the Euler formula. So we say first we need to find an expression for cosine of x from the Euler formula. Okay, what is the Euler formula? The Euler formula say e to the power of ix equal I times sine of x plus cosine of x. Excellent. Now here's the insane part that you can do to get cosine of x. This is where you start, right? Now you compute e to the power I times negative x. What does it equal to? Equal to I times sine of negative x plus cosine of negative x. And what does that equal to again? It also equal to negative I sine of x plus cosine of x. Why? The reason why is because you recall that sine of x is, let's see, sine of x is just sine of 0 minus x, and it is negative sine x. If we use the formula we have derived in the second video, sine a minus b. Similarly, cosine of this is negative x. It's just cosine of 0 minus x, and you should get cosine of x. So you use the cosine a minus b, sine a minus b formula, which is derived in the second video of the series, I believe. Okay, so you get here, what you're gonna do? You're gonna add them up and divide by 2. Okay, so you say e to the power ix plus e to the power negative ix equal to what? Equal to I sine x plus cosine of x minus I sine x plus cosine of x, right? So that means say e to the power ix plus e to the power negative x equal to 2 cosine of x. Okay, wonderful. So what is cos of x? Cosine of x is e to the power ix plus e to the power negative ix over 2. Wonderful. So now how is we going to proceed? Remember our goal is to show that cosine k pi equal negative 1 to the power k, right? And now we have the formula for cosine of x from the Euler formula. We can proceed to use this lemma, or formula we just derived, or let's say we can use this lemma. Okay, so let's go ahead and write out cosine of k pi is equal to e to the power I k pi plus e to the power negative I k pi over 2. Okay, what does that equal to? If you time both sides by e to the power a k pi plus e to the power negative I k pi times e I k pi over 2 times e to the power I k pi. And if you find it out, you should get e to the power a k pi square plus 1 over 2 times e to the power I k pi equal to e to the power of I 2k pi plus 1 over 2 times e to the power I k pi. Right? Okay, you are here. What you gonna do next? Let's see. All right. So let's go ahead and evaluate e to the power 2 ik pi and see what we get. Okay, so e to the power of 2 I 2k pi will be equal to, if you remember the formula, is just I times sine of 2k pi oh, my bad, I'm sorry. Okay, let me calm down a bit. Okay, now we need to, in order to finish this time, we need to evaluate e to the power I 2k pi and e to the power I k pi. But first, let's evaluate e to the power ik. What is e to the power ik? Oh, my bad. E to the power of I pi. So e to the power I pi is just I sine pi times cosine pi, right? You agree with me? Okay, and if you recall, sine pi is 0 and cosine of sine cosine x negative 1 1. So negative 180, you spin, you at this point, you are here. So your cosine negative 1 and your sine 0. So it will be I times 0 plus negative 1, so it will be negative 1. Okay, wonderful. E to the power ik pi, it will be e to the power I pi to the power k, which is negative 1 to the power k, which we already show that e to the power of I pi is negative 1. E to the power I 2k pi is just going to be e to the power I pi to the power 2k, which is negative 1 to the power 2k, with this negative 1 to the power 2 first, and then k, which is 1 to the power k, and which is 1. Okay, so we come here, we can plug into our sum. We can plug in our expression now. So you get cosine of k pi equal to e to the power I 2k pi, which is 1, right? Plus 1 over 2 times e to the power k pi, which is negative 1 to the power k. So this is 2 over 2 negative 1 to the power k. So this is going to be 1 over negative 1 to the power k, which is, so recall that 1 is negative 1 to the power 2k, negative 1 to the power k here. The reason why here. And so you get negative 1 to the power 2k minus k, which is negative 1 to the power k. Okay, so here, everyone, this is what we have. We have demonstrated cos k pi is equal to negative 1 to the power k. Oh, and here, so we have some time. What about sine of k pi? Can we find it now? Of course. So you have e to the power I k pi equal to I times sine of k pi plus cosine of k pi, right? What's the e to the power I k pi? E to the power I k pi is negative 1 over k. We have that. Negative 1 over k equal to I sine k pi plus cosine k pi. Do we have that? Yes, we do. It's negative 1 over k is a theorem we just proved, and now we can use it wherever we want. Okay, and then if you subtract both sides, you get I sine k pi equal 0. So you can say sine k pi equals 0. So how do you apply this formula? The way you apply this formula is that cosine of 2 pi, it's just negative 1 over 1 square, which is 1. Cosine of 3 pi, right, application equal to negative 1 over 3, which is negative 1. Sine of 2 pi is 0. Sine of pi equals 0. Sum any integer number times pi is 0. Okay, so this is the powerful result we have. And thank you everyone for your attention. In the next video, I will demonstrate how to convert a sum of two imaginary exponential number to multiplication. Okay, stay tuned. See you in the next video.